Swayam Prabha. Digital India. Educated India.
Good morning and welcome back to lecture number 23, part 1 on the topic cold storage design for positive temperature application. So, this is a very interesting topic. In the next few lectures from now on, we will be designing the cold storage for two types of applications. One is positive temperature, another one is negative temperature. So, under positive temperature applications, I would be taking I will be solving two numerical questions. And similarly, under negative temperature applications, pertaining to negative temperature applications, so 2 to 3 design problems I will be solving. At the end of this particular lectures, especially this from lecture number 23 to next 3 to 4 lectures, the learners will get a very good idea about how to design a cold storage. Perhaps it can motivate some of the learners. They want to start their entrepreneurship pertaining to the cold room or cold storage facility. So let us move to the first one. Before seeing the numerical question, when I say positive temperature application, it refers to the storage of products above 0 degrees centigrade. That is, the products which are mentioned, dairy products, fruits and vegetables, pharmaceutical products, horticulture, floriculture. Most of these are stored in the temperature, say about 2 to 6 or 7 degree centigrade. 2 to 6 or 7 degree centigrade, less than 10 degrees centigrade. So, some of them have storage temperature of 2 to 5 degree centigrade, to be more specific. Design a cold storage to store potatoes for the following conditions. Normally, the problems related to the design of cold storage, the details given or the conditions given, it will run into quite few slides, because a lot of, as we have discussed in the cold storage requirements, there are about 13 points like location, what is the ambient condition, dry bulb temperature, wet bulb temperature, what kind of product to be stored, specific properties of that thermal properties of the product, what is the dimensions of the door, etc. First one is outside condition, that is 45 degree dry bulb and 30 degree wet bulb temperature. Temperature inside the cold room is 15 degrees centigrade and 90% RH, that has to be maintained. The temperature at which the product is to be loaded is 25 degrees centigrade. Weight of each bag is 50 kg. Total storage capacity is 4 rooms, each of 1250 tons. The total quantity is 1250 multiplied by 1000 in terms of kilograms. Size of the room or the chamber is given as length is 14 meter, width is 8 meter, height is 12 meter. Loading rate is 4% of the total capacity per day. This point I was mentioning when I was explaining the theory in one of the earlier lecture. On an average, not more than 4 to 5% of the total storage capacity of the product to be loaded per day. Pull down temperature and time is 15 degrees centigrade in 1 day. Compressor running hours is 20 hours per day. Insulation polyurethane foam, that is puff. Thickness of the insulation is 100 mm. Specific heat capacity above freezing. Since we are designing the cold storage for a positive temperature application, so there will be only one specific heat capacity which is above the freezing point. Respiration heat 0.018 watts per kg. Number of fans, 8 fans are used, each 0.75 kilowatt. Number of occupants, 4. Lighting intensity is 10 watts per meter square and safety factor is 10%. So let us write the given data. Product is given data. So the detailed solutions are given in the PowerPoint presentation. As I explain, as I write, it will be easy for the learners to understand easily and also to refer when they want to refer at a later stage. So the product to be stored is potatoes. Outside condition is given. So due to time constraint, I may not be able to write all the given data. So let me write the few datas which are given. Insulation is puff. Some of the data given in the problem, I will substitute directly. Dimensions, chamber dimension. So it is 14 meter, that is length, into, let me check, 14, 8, 12. 14 meter into 8 meter into 12 meter. That is height. Length into width into height. Insulation used is polyurethane foam, that is puff. Thickness is, insulation thickness is represented by the letter small x. Small x is equal to 100 millimeter, which is equal to 0.1 meter. Specific capacity above freezing is given as 3.43. 3.43. CP value above freezing. This is above freezing. 3.43 kilojoule per kg Kelvin. Respiration heat is given 0.018 watts per kg. Heat of respiration heat, that is equal to 0.018 watts per kg of potato. Loading rate is given, that is 4% of the total capacity. So there are 4 rooms are there of equal storage capacity. Each room has a storage capacity of 1250 tons. 1250 tons. So loading rate is 4% of the total capacity. So with this data, I will be calculating the M value. So M is equal to 4% of total storage capacity. 4% of total storage capacity, which is equal to 4% of 1250 tons. So which is equal to 4 by 100 into 1250. It comes to, M is equal to, it comes to 50 tons, I think. It comes to 50 tons. M is equal to 50 tons. That is per day. So this is tons per day. So that is equal to 50 tons per day, which is equal to 50 into 1000 kg per day. So in the previous lectures, we have solved numerical problems pertaining to a particular type of cooling load. We solve problems based on transmission load separately, product load, in the product load with respiration and without respiration, that is a live product and a dead product, and I solved one problem based on the infiltration load also. When we design the cold storage, based on the data given, we need to calculate the various load components, such transmission load, product load, infiltration load, ventilation load, equipment load. lighting load, etc. So first let us calculate so these are all the important data which I have written. There are other data, light intensity, all those things, number of fans used are there. So this data I will be substituting directly at the appropriate places in the formula. So let us first calculate the transmission load. First one is transmission load. Transmission load, that is QT, is equal to UA delta T. UA delta T. This is equal to U equal to K by X. K by X into A into delta T. K value is not given, X value is given. X value is given in the problem. But we know that material used to make the insulation, that is puff. So I will be referring the data book. So from ISHRE, cold storage, design guidebook, so let us go to the table. So I will be using this table 2.1, and this is the same table which I used when I was solving a numerical question based on transmission load. So this is the SI unit values of K. This is K. So the given material is polyurethane board. This is the material which is given, polyurethane board. So the values are, it is given in the range 0.023 to 0.026. So I will take the value this way, 0.023. So from table number 2.1, table number 2.1. Table 2.1 for polyurethane foam. Polyurethane foam or board, both are same. K is equal to 0.023 watts per meter Kelvin. K equal to 0.023 watts per meter Kelvin. So that's what I have written here. K is equal to 0.023 watts per meter Kelvin. Now I will be substituting this area. We know the dimensions of the chamber are given. Delta T is, the outside condition is 45 degree dry bulb temperature. Cold room temperature is 15 degree. So delta T is 45 minus 15. 45 minus 15. So substituting the values, therefore QT is equal to, before substituting the values, let me expand this one. We will substitute the values. K is, that is K by X into area is 2 times into length into width plus width into height plus height into length into height into delta T. Now substituting the values, K is 0.023, which we have found from table number 2.1. Okay, this is the value of K. X is given 0.1 meter, 0.1, 2 into, the dimensions are, L is 14 meter. This is the dimensions given. 14, 8 and 12. 14, 8 and 12. So 14 into 8 plus 8 into 12 plus 14 into 12. And delta T is 45 minus 15. 45 minus 15. So let me write it here. Outside temperature is equal to 45 degrees centigrade. Cold room temperature or inside condition, all these are same. cold room temperature is equal to 15 degrees centigrade. So this is delta T, this is delta T. So substituting the values, we will get 5.2 kilowatt. 5.2 transmission load comes to 5.2 kilowatt. So QT is equal to 5.2 kilowatt. Next, let us calculate the product load. Product load. The product is, the application is a positive temperature application. Hence, the product is stored above 0 degrees centigrade. That is above freezing. So, we need to calculate Q1 and only. Q2 and Q3 will not be applicable. The latent heat and the sensible heat below freezing, Q3 will not be applicable for this case. Q2 and Q3 will be equal to 0. And of course, respiration load will be there because potato is a vegetable, being a vegetable is a live product. So, it has got the respiration. Now, let us take sensible heat above freezing, that is Q1 is equal to mass of the product into Cp into, so here let me use the notation which let me check what is the temperature T1 or T2. It is T1 minus Tf. And what is the delta T? The product is cooled from, this is the product loading temperature. This is T1. Product loading temperature is T1. And it is cooled up to the cold room temperature of 15 degrees centigrade. So, the product is cooled from 25 to 15. That is pull down temperature and time is 15 degree. So, T1 minus Tf. So, here Tf is not exactly the freezing point, freezing temperature. Since the product is cooled above freezing, so you have to take the temperature up to which it is cooled. It is not exactly the freezing temperature. So, here it is nothing but this is 15 degrees centigrade and this is product loading temperature. Product loading temperature. So, mass is 50 tons multiplied by 1000 will give in kg. Cp value is given 3.43. Mass we have found here. So, into 3.43 into 25 minus 15. That is sensible cooling. So, sensible heat above freezing, that is cooling from 25 to 15. Let me write it as a sensible heat itself. Above freezing, that is cooling from 25 degrees centigrade to 15 degrees centigrade. So, when we calculate, we get Q1 is equal to, so because the mass is kilograms per day, so I am getting this value 1716500 kilojoules per day. 1716500 kilojoules per day, because this is kg per day. This is in kg per day. So, here also per day will come. So, 1716500 kilojoules divided by per day 24 hours into 3600 seconds. So, you will get in kilowatts. You will get it in kilowatts. So, 19.9 kilowatts. 19.9 kilowatts. If you want here, you can write T1 is equal to 25 degree centigrade. Here Tf is equal to 15 degrees centigrade above freezing. It is not freezing temperature, above freezing. 19.9 kilowatt. So this is to convert day into seconds. Q1. Q2 is equal to Q2 equal to 0 and Q3 is equal to 0. Since the product is stored above the freezing point, is stored above is stored above the freezing point. Now let us calculate the respiration load. Respiration load Q4. Respiration load is Q4. So the formula is mass into heat of respiration. Mass is that is 4% of 1250 tons, that is 50 tons. 50 into 1000, that is mass, into heat of respiration, I think it is 0.018. So here, do not substitute the mass in, not only here, even in the previous step, do not substitute the mass in tons, we have to substitute in kg. And here the heat of respiration is given in terms of watts per kg. So kg and kg will get cancelled, we will get the unit in watts or kilowatts. So if you see Q4, that is 0.0. Here one small point need to be considered. There one assumption to be done. Assuming one assumption have to be made. Assuming the remaining quantity of potatoes are in store and the refrigeration load on the last day of loading is considered. Because the products are loaded in batches. Since the products are loaded in batches. So this assumption I am making. So here M will be not 50 tons, it will be out of the total tons per room. Each room has a storage capacity of 1250 tons. There are 4 rooms. So total capacity is 5000 tons divided by 4250 tons. Out of 1250, 50 is already, that is 4% of the storage capacity only is loaded every day. That means out of 1250, 50 tons of potatoes are loaded this one. So assuming that the 1200 tons are in store and refrigeration load on the last day of the loading is considered. That means we have to take the remaining quantity, that is 1200. And W heat of respiration is given as 0.018. Okay, so let us make this assumption. So here M is equal to 1250 tons minus 50 tons, that is equal to 1200 tons, which is equal to 1200 into 1000 kg. So Q4 is equal to 1200 into 1000 multiplied by 0.018. So it comes to 21.6 kilowatts. 21.6 kilowatts. 21.6 kilowatt. Assuming that the remaining potatoes are in store and the refrigeration load on the last day of loading. So this is very, very important assumption. Okay, so that's what I have underlined here also. Assuming the remaining 1,200 tons of are stored in the store and the refrigerator load on the last day of loading is considered. Now, when we add Q1, Q2, Q3, Q4, we will get the total product load. Therefore, product load Q suffix P is equal to Q1 plus Q2 plus Q3 plus Q4, which is equal to Q1 is in the previous slide, that is 19.9 kilowatt, 19.9. Q2 is 0, Q2 and Q3 are 0, Q2 and Q3 are 0, Q4 is 21.6. So when we add, we will get, I think it comes around 45.5 kilowatt. So the product 41.5, not 45.5, 41.5 kilowatt. Out of the total loads, 5 to 6 loads are there. We have calculated the transmission load and the product load. I will stop this lecture at this point. It will be continued in the next lecture. Thank you.